So we've covered reactions with the halides, both on the basic conditions, i.e. enolates with dihalides, such as reactions with the haloform reactions. We've also seen an acidic event. Now we're looking at coupling at the alpha carbon. This section will look at coupling with the alkyl halides, and in the future chapters we'll look at reactions with aldehydes and ketones, esters, and of course the beta attack at the enols, i.e. the Michael addition. So you remind yourself, or you should remind yourself of what this attack looks like, because you have here deprotonation of the alpha carbon to realize your enolates. Your enolate will then attack your alkyl halide. Realize your alkyl halide got to be primary or secondary, because it is a bimolecular event with that eventual removal of the leaving group. So here is the new carbon-carbon bonds. We can use this flavor, yes, of the enolates. You can see here, for example, once you reform the carbonyl, then of course the attack occurs by this nucleophilic pi system. But I want you to focus on this mechanism because this one is the simplest to envisage. We can also form enolates, of course, with esters and nitriles, and realize that once deprotonation occurs, then we can then use that alpha carbon for the same nucleophilic attack. Why don't you go ahead and try to generate the resonance structures of each of these enolates. So here's a question. The question is, select the alkylation product after I deprotonate our carbon here. Yeah, so go ahead and do that for us, and then we can review this in class. This is another species, is a common analgesic that everybody uses, and ibuprofen, I'm sure you know about it. But you can see that we have here a reduction, and followed by the phosphorus tribromide with nucleophilic attack by the cyanide, yeah, and then of course remind yourself the reason why we use LDA, and then note that we definitely will have this type of alkylation, and of course you can see there's some sort of quenching with heat. Go ahead and work on that, identify the products. If you can even do some mechanism, say for example that occurs here and here after B to get C, then that would be really helpful. The next reaction, or the final section in the carbon, is that of reactions that involve the malonic ester synthesis and the acetoacetic ester synthesis. Both are taking advantage of the decarboxylation of beta-keto acid. So we talked about the beta-carbonyl before, how acidic this proton here at the alpha carbon is, because we can generate 3 resonance structures from there. So what happens then is that if we have an ester here, so instead of an ester there, then of course you can see that we can deprotonate here and do alkylations, etc., etc. once sulfonification occurs, yeah, we can remove that, and then we have a unique property with this beta acid that we want to talk about. If, remind yourself, if this position here is OH, then that is the malonic acid. So we can start off with a malonic ester. And if that position is a CH3, then of course that would be the aceto. See, aceto, acetic, yeah, ester. The unique property of the beta esters is that once you sulfonificate, then you end up with the beta acid, and the beta acids undergo decarboxylation on heating. Look carefully, because here's the beta carbon in both the malonic species and the acetoacetic acid species. And I'll now show you a mechanism which is a pericyclic mechanism that occurs. So it's quite simply put, you can see that this will deteriorate, say move into this space. Then we'll have a disconnect, i.e. there'll be cleavage of that carbon-carbon bond. And here we have the oxygen adding to the proton. The result is that there is a loss of carbon dioxide and the formation of an enol. We know that an enol will tautomerize to give us a carbon atom. So in the case of the malonic acid, on heating we end up with an acid group. In the case of the acetoacetic acids, on heating, the tautomerized species, of course, will give us a methyl ketone, i.e. an acetyl group. So the question here is, which diacid would most readily lose carbon dioxide? And again, what you need to do is pause and try to elucidate what we are striving for. So our first reaction that we'll cover is the malonic ester synthesis. We start off with the malonic ester. You can see it's a derivative of malonic acid. In this case, we flanked it with two ethyl groups, so it's the ethyl, diethyl malonic ester. And we react, after deprotonation, we react it with an alkyl halide. And the result is we end up with an acid. You can see in the acid, really, it's a 2-carbon coupling. 2 additional carbons has been added. I also have the possibility, because there's 2 protons here, I also have the possibility of adding another R group, and so I end up with 2 R groups on this alpha carbon. So here's the general plan. You can see we have the malonic ester, in this case diethyl malonate, and we're going to deprotonate and react with our alkyl halide. So here is the coupling. We can sulfonificate these ester groups to give us the diacid. Now realize that the diacid is a alpha beta acid. So the beta acid on heating will give you your carboxylic acid. So the coupling that took place between these two yeah, has added 2 carbons to your alkyl group. We do not have to work up with the acidification, isoponification, and heats. We could go straight ahead and add another stoichiometric amount of base with another mole of an alkyl halide, and now we have 2 alkyl groups on our alpha carbon. Thus, when we saponificate and heat, we end up with a carboxylic acid with 2 alkyl groups coupled to the carbon. So we can ask a simple question like this. And I would love you to elucidate this, and then we can look at it closer during our discussion sessions in class. So here's our mechanism, or we can generate a mechanism if you don't mind putting the arrows for me, but you can see that what we have the first step is the deprotonation of your malonate. And then, of course, you have the nucleophilic attack on your alkyl group. Remember, this is a bimolecular event, so it has to be primary or secondary, and primary works best. So there is your alkylation product. So saponification, i.e. hydrolysis of your ester, result in your diacid. Your diacid will then decarboxylate to give you that enolic form, which tautomerizes to give you your acid. Realize that this will be the final part of your acid, and so that is your final acid. So I can ask you to give me the product and mechanism for the following sequence of reagents, and please do that for us, and then we can talk about it during our discussions. The retrosynth of the malonic esters is quite simple. You got an acid, right? And you got to determine what pathway did you take from the malonic ester to give you said acid, right? So you immediately identify the alpha carbon of said acid, and then of course realize that it is a 2-step process. So firstly, you identify the alpha carbon, identify all alkyl group bonded to such alpha carbon. So in this case, we have one R group. And so we can break the molecule into the 2 components, or 3 components if it was disubstituted alkyl groups. And so here we have the alkyl halide that we started with, and of course the malonic ester. Then we can work from there. So a question like this, for example, which I would like you to do, during our discussion sessions, does have 2 alkyl groups, involved in its reaction, right? So if you look carefully, this is benzyl butanoic acid. From there, then you can go ahead and show us how this is synthesized from the malonic ester. Intramolecular malonic ester synth can be used to generate cyclic carboxylic acids. So herein, if we use dibromobutane, 1,4-dibromobutane, then if we deprotonate our malonic ester, then of course we can attack this dihalide. The first attack would realize this substituted species, but we still have this halide present, and therefore deprotonation of the other alpha carbon realizes an intramolecular attack, which then gives us a ring. And note, our ring has a diester, so we still do have that beta-ester, which can then be saponificated and heated to give us our diacid, to give us our acid. So in this case here, we have the cyclopentane carboxylic acid. What I would like you to do is to pause here, take these problem sets down, and work on them. So in the first column, we have the reaction plus the quench. In the second column, then we have saponification. So therefore, in that first column, we do have the alkylated malonic ester. In the second column, we should have the diacid. And in the third column, we should have our acid. So next, we'll look at the acetoester synthesis. And in this case, you can see that if we're using the ethyl acetoacetates, then of course it's going to be a 3-carbon coupling. 3 additional carbons. If we're using the acetyl species. So really, you got your alkyl halide, you're going to deprotonate, and this is your, after deprotonation, you attack the alkyl halide. You can see that we can have a 1 alkyl group, or we can have on the alpha carbon 2 alkyl groups. But the result is, of course, a methyl ketone, and it's 3 additional carbons in the case of the ethyl acetoacetates. Here's where the cleavage will occur. So I could ask a simple question like this. Recognize, there's a dihalide there, there's 2 protons here. But the point is that this, of course, is your acetyl acetate, right? So it's your acetoacetic ester. See? There's your acetic group, ester. Okay? So let's move on. The mechanism is, since we've done the malonic ester already, then this mechanism is quite simple to figure out, because you can deprotonate, and then of course you attack, so you add 1 mole of your alkyl group here, and then of course you can saponificate, and then heating, I should put the heat here instead of here, but heating realizes your 3-carbon coupling, your methyl ketone, you see, methyl ketone. Instead of working it up with the saponification and heat, we could add another mole of the alkyl halide. So now we have 2 moles of alkyl on your alpha carbon, and saponification realizes the diacid. It is a beta acid, and so on heating, you end up with loss of the carbon dioxide, and herein you have your methyl ketone. It's a 3-carbon coupling, yeah? That was your alpha carbon. Let's have a look. So we can ask a question like this. We can do this one quite simply put, because you can see we can deprotonate one of these guys and add this fella here. It's a 2-carbon. And of course, you're going to end up with coupling here, yeah, and this is your 1, 2, 3. So you're looking for something with 5 carbons. The mechanism, of course, looks like this. You see your starting material is the ethyl acetoacetate, and you can see the deprotonation that will take place here with the base. Remind yourself that this is the most acidic proton, not this guy, because this only has 2 resonance structures, while deprotonate here you'll get 3 resonance structures. The attack then, of course, will occur bimolecular on that alkyl halide. So the alkylated product is, of course, your beta-ester, which can then be saponificated, i.e. hydrolysis. And you can see now that this one is easier to envision, because now you can see that there's only one place to remove that acid. That's your beta acid. So the decarboxylation realizes your methyl ketone. So here we have a mechanism for 4-phenylbutylene. What you got to realize, it's from the acetoacetic ester, so we should try to recognize the alkyl groups that are attached to the methyl ketone. So the mechanism will start off with, yes, deprotonation of our acetoacetic ester, and before we continue, I really want you to draw this compound. We'll talk about this in class. Of course, we talked about, the dialkylation. So what we can do is we can look at this species and select the product form from the following reactions. And you can see we have 2 alkyl groups there. So why don't you go ahead and do this, and we can discuss this the next time we meet. Here we're looking at the retrosynthesis, via the acetoester synth. And what you would do here is, of course, draw the 3-propyl hex 5 into Rome. So that's what you would do. That's your target molecule. And those are the alkyl groups that are attached to it. So from there, go ahead and do that synthesis for us, and we will continue in class. What about this one? What alkyl halides are needed to prepare each ketone using the acetic ester synth? Yeah, we can see immediately that most likely, because we form the ring system, we therefore need a dihalide. So think about the dihalide that you would have once you think of these disconnects. This, of course, being your alpha carbon. So work on this one, and realize that that is the end of our work for this chapter, and then we'll push on later to start looking at the enolates, i.e. we'll start looking at condensation reactions.